From section 1.7 when we learn about inverse functions. Basically what an inverse function is a function that undoes some other function. So the way to think about this is you start out with some function, maybe f of x equals 2x. This machine doubles the input. So if 4 goes in, 8 comes out. If negative 5 comes in, 10 comes out. For this machine, for this function, I can define an inverse function. The notation that I'll use to talk about my inverse function is this right here. This doesn't mean f raised up to the -1 power. This is just a symbol, f with a -1 up in the superscript, that represents the inverse function. And the inverse function for this function is the function that undoes what this function did. Well, this function, what it did was it doubled all the inputs. So what the inverse function will do is it'll cut all the inputs in half. The inverse of this function, the inverse of this function is this function. That's it. That's an inverse function. Turns out that that seemingly easy concept has a lot to it. So much so that let's go through and talk about these more generally. I drew this picture because I think this picture really helps me anyways think about what an inverse function is. So this is my regular picture for a function where I take some input, usually use the letter x for it, and I put it into my function, and what comes out is f of x. So I could take a number like 3, put it into my function, maybe 9 comes out, fine. The inverse function is the machine that takes that output and undoes what the function did to take you right back to the input here. So you can picture that up here. I put the number 5 in and my doubling machine made it 10. So the inverse function must take that 10 and undo the doubling to give me back 5. That's what the inverse function does. This diagram helps me a whole lot because the important implications of this diagram, which is basically what I use to think about the definition of an inverse function, are these four. The first one, you can only define an inverse function for a one-to-one function. Wait a minute, it's been a little while since we talked about one-to-one functions, and what do you mean you can only define a function? Okay, remember back to 1.1. There's this really important criteria for a function. And the important criteria was that every single element in the domain must have exactly one element associated in the range. It is not a function if I put the number 3 in and the numbers 5 and 7 both come out. It's not a function if that happens. What can happen is I can have two different inputs giving me the same output. So for example, maybe I put 2 in and 5 comes out, and I put 10 in and 5 comes out. That's totally fine. That's a function. It's just not a one-to-one function. But if my function up here is not a one-to-one function, so what that means is there's two different inputs over here that I put in that give me the exact same output, then think about trying to define the inverse function. It's totally fine to have two inputs with one output, but that one output, when I put it into the inverse function, would have to give me two things. There'd have to be two outputs from this inverse function to undo what the function did. So if there's two different inputs for the function leading to one output, that would give you one input for the inverse function leading to two different outputs. If the function is not one-to-one, then when you try to define the inverse function, you'll come up with something that's not even a function. So it's only fair to ask somebody to define an inverse function if that function is one-to-one. A question like f of x equals x squared, find f inverse of x, is an unfair question. You can't do it because x squared is not a one-to-one function. That's the first important implication of this definition. The second one is just noticing that the inverse function switches the inputs and the outputs. So, for example, if f of 2 equals 5, then f inverse of 5 must be equal to 2. Right? Because this statement right here is saying that when you put 2 in, 5 comes out up here. But the inverse function is defined so that if you take that output from the function, which is 5, and use it as the input in your inverse function, 2 must come out. In other words, f inverse of 5 equals 2. If 2, 5 is an input-output pair in my function, 5, 2 must be an input-output pair in my inverse function. That'll be really useful later on when we talk about the graphs of inverse functions. Inverse functions switch the inputs and the outputs of the function, I guess. 3 is very close to 2. Maybe I could have merged these into 1. 3 says that the numbers you're allowed to put into the function are what are called the domain of the function. And the numbers that can come out of the function are what are called the range of the function. But it's the things that come out of the function which go into the inverse function. So it's the range of the function that is the domain of the inverse function. And similarly, the things that come out of the inverse function is exactly the things that go into the function. So the range of the inverse function is the domain of the function. Inverse functions switch the domain and the range from the function. 2 and 3 are very similar. 2 just talks about a single input-output. 3 talks about all of the inputs and the outputs, aka the domain and the range. The fourth one, this recycling property, tells you that anytime you compose a function and its inverse, you always get x. What I mean by that is if I take x and I put it into the composite function, it means this. It means f inverse of f of x or f of f inverse of x. Either of these two things are equal to x. You know, well, that's a lot of symbols going on there. Composition, I just learned that a couple sections ago. I'm supposed to be an expert with this. I think I can prove all this with this picture right here. If I take something, and maybe I call it x, and put it into my function and then into my inverse function, that's this picture right here. You put it into your function, and then what comes out of that goes into your inverse function. If you take something and put it into your function and then into your inverse function, what would come out would be x. It would be exactly what you started with. The function messes it up, the inverse function unmesses it up and gets you back to where you start. Take something, put it into your function, then into your inverse function, what comes out is exactly what you started with. Same thing if you take something and put it into your inverse function. If I take something over here and put it into this machine, and then what comes out goes into this machine, I'll get right back to where I started. Take something, put it into your inverse function, that output goes into your function, what you get out of that function will be exactly what you started with here. That's this fourth property here. That hits on this first thing. The next two I want to talk about. Finding the inverse of a one-to-one function. Let's say I give you a function like f of x equals x plus 3 divided by, how about x over x plus 3? Fine. This is a perfectly good function right here. I'm going to ask you to find f inverse of x. The minute I ask you to find f inverse of x, I'm implying that this is a one-to-one function, because remember, you can only define an inverse function if the function itself is one-to-one. This is a one-to-one function. You can graph it, you can run the horizontal line test. This is a one-to-one function, trust me. So how do you find the inverse of this? How do you find the machine that undoes what this does? Right? If I put the number, I don't know, 2 into this machine, what comes out would be 2/5. So what's the machine that when I put 2/5 into it, 2 comes out? It's really hard. You might think you can just look at this and figure it out. Maybe if you're some super smart person, you can. But generally speaking, it's really hard to do, and I can probably come up with a function that's so hard that you wouldn't be able to. So let me show you a series of steps that will always let you figure out the inverse of a function. Step 1, change f of x into a y. Why do you do that? Because I'm going to do a lot of algebra, and I don't feel comfortable doing an algebra with this f of x symbol. The f of x is just the y. Just change it to a y so it's easier to do algebra. You're not really changing anything. That's step 1. Step 2, everywhere you see a y, change it into an x. Everywhere you see an x, change it into a y. Why? Just because? Well, I don't know. This is the short video, so maybe yes, just because. But really the reason why is this is an equation that represents your function, and I want an equation that represents my inverse function. But remember that a function and an inverse function just switch the inputs and the outputs. So all I have to do to get an inverse function equation from a function equation is switch all the inputs and the outputs. Change the x's to y's, y's to x's. That gets me here. You might be trying to save time and realize that you could have gone straight from here all the way down to here. Hey, feel free if you want to. Change f of x into x and x into y. You can do that. I think it's more intuitive to go through these steps, but you do whatever you want to do. The next step, solve for y. That's the step that, depending on the original function, can be really easy or really hard. Imagine doing that up here. Change f of x into a y, so I got y equals 2x. Change the x's into the y's and the y's into the x's. Now I got x equals 2y. Solve for y, no problem, divide by 2. I get y equals 1/2 x, which ends up being the inverse function down here. Super easy. Down here it's a lot harder. Solving this for y is challenging. The way you do it is first let's get rid of the fraction. So I'll multiply both sides by y plus 3. And you're like, I solved for y, done. No, you didn't, because you can't solve for y in terms of y. You can't have a y in your answer. It's like when you, well, I won't even talk about what that's like. You're trying to solve for y, you cannot have a y in the answer. So what you do is you have to get all the terms with y's in them on one side of an equation. And it's hard to move the pieces around with the parentheses. So what you might choose to do is first get rid of the parentheses. So take this x and distribute it through. Then collect all the terms that have y's in them on one side of the equation. something like this. I subtracted xy from both sides. Now all my y's are over here on the right. And the reason you do that is now you can factor out a y. And what you've managed to do through the magic or power of algebra is you've rewritten some equation that have multiple y's in it with an equation that only has one y in it, this one right here. So I can solve this one for y by dividing both sides by 1 minus x. And I get 3x divided by 1 minus x. This is the inverse function. That's not entirely true. This is an equation that represents the inverse function. Y is something you kind of created in this process. It asked me to find f inverse of x. So really you should take this last step where you write this in function notation instead of just as an equation. Although if you leave your answer like this, I'm going to know what you mean. But probably a good idea to get to here. Note that looking at this, it would have been very challenging to immediately come up with this. I mean, they're similar. There's a 3 here and a 3 here, and plus change to minus somehow. But now the 3's on the top instead of the bottom. It's hard to look at this and figure out what this is. But these series of steps will always work. This is just for one example, but I'll go through more examples as I go through the chapter to show you how to do this process on different functions. The steps will remain the same. It'll be this process where you're solving for y that'll be different depending on the equation you have. Last thing I want to do is graph an inverse function. So let's see. I'm just going to arbitrarily draw a function. Maybe I'll do it on this one. And that's a bit of a lie. I don't want to just draw something arbitrarily. Because if I draw something arbitrarily, it might not be 1-to-1. And I have to make sure what I draw is 1-to-1 because I can only come up with the inverse of a function that's 1-to-1. And so here's my graph of some function. Maybe I'll call it g in blue here. And what I want to do in red is graph g inverse. And there's a few ways you can do that. You can first take advantage of this second implication that all my inverse function does is it switches the inputs and the outputs. So geometrically, it takes any point, like, I don't know, this point right here that appears to have an x-coordinate of 1.5 and a y-coordinate of 0, and it switches it. Instead of being 1.5 comma 0, it goes to 0, 1.5. Goes up here. And this point right, I don't know, here maybe, appears to be at what, 2.5, 3.5. So I'm going to move that so that it appears at 3.5, 2.5. There'd be some dot right here. Whoa, how am I going to connect these dots? Well, you could do that a whole bunch. You could figure out all the different, here's -2, -3. So this should be at -3, -2. Fine, that one should go there. You can try your best to connect the dots, but it's hard to know what it looks like. So there's another way you can do it. Especially for complicated functions like this, it helps. Switching the x and the y coordinates is equivalent to reflecting over the line y equals x. This right here in green is the line y equals x. And it turns out that switching the x and the y coordinates is equivalent to just reflecting over this line. And maybe you can kind of see that now that that line's in there. This point moved to here. Oh, it just kind of bounced across this line. This point moved to here. This point moved to here. I could draw a bunch more points, or I could just try my best to draw this kind of as a mirror image. So let's see, maybe it starts out something like this, maybe even steeper. Something like this, and it goes through this point, and then it kind of bubbles up here, it goes through here, and it crosses over there, it goes through here, and crosses over again, and looks something like that. Not perfect, but not bad. This would be a graph of G inverse, which I like doing this both because it's nice to be able to get the graph, serves as a nice check. If you're not sure if you did this one right, you could check it by graphing this and then graphing this and seeing if it really did reflect over this line. While I'm here, another way you could check this, note, check, could check, you don't have to do it, by seeing that f of f inverse of x really does equal x, or that f inverse of f of x equals x. Remember, that was our fourth criteria here. It says when you run a function and its inverse one after another, when you compose them together, you get right back where you started. It's our recycling criteria. I should be able to check that algebraically. Because I can compose these together. I could take f inverse of x, this thing, and put it in here. Everywhere I see an x, replace it with 3x divided by 1 minus x. It'd be a mess, but if I simplified those fractions inside fractions, I should get exactly x as my output. And if I do, that'd be a nice little check that I did things right. I did that check in the other video, and I'll probably go through that check in some examples, but I think for the sake of this being a short video, I'll end this here.